The last experiment of the lab manual, at least in 2015, we're going to take benzoic acid and then we're going to switch it through reduction to benzyl alcohol. So we'll try and make this quick for you guys. Obviously, just like all acids, when you look in Pavia, Pavia might label across the top pointing at this as your OH stretch. Other books will just sort of circle this representing the bulk of this overwhelming absorption comes from the OH stretch of a carboxylic acid. Whether you start labeling any of these tips, sometimes it's a little sketchy. That can legitimately be part of the CH stretch. But if that was so true, then why are we seeing so many strong peaks at less than 300? Because there is no sp3 carbons with hydrogens on it. So that's why I'm equally skeptical of pointing at 3070 in this particular one and saying, oh, that absorption right there has to be an sp2 carbon with a hydrogen stretch. They're buried in there, I'm sure, for this compound. But you don't have to label those in this particular one. The carbonyl, 1685, that's obviously the C double bond O stretch. There's an aromatic ring, which means, as usual, usually you see 3 to 4 peaks, 1600, one just at 1582, and then usually the 1453. These three are usually considered to be the C double bond C stretch of an aromatic ring. It's a mono-substituted ring, so we expect 2 peaks if we can see them. Now, thankfully, we can easily see 707, 666. Wow, I didn't plan that. These two would be your mono-substituted, out of plane bend of a mono-substituted ring. As we go down to benzyl alcohol, same region, benzyl alcohol is a mono-substituted one. You see the same 2 strong absorptions, mono-substituted, out of plane bend. And yes, this is the benzyl alcohol, so we're looking for a CO stretch of a alcohol. 1053, the most strongest one there is probably it. You could actually circle both. One could be symmetric, the other asymmetric. We also have an aromatic ring. 1607, very small, and then we jump up to a 1596. 1453 could be considered as your C double bond C aromatic stretch. We have our OH stretch of the alcohol, 3400 clearly. We see at 2976, 2872 at least here, those are your sp3 carbons with a hydrogen stretching away. Just to the left of 3000 right here are your sp2 hybridized carbons of the aromatic ring with a hydrogen stretching. So that handles the IR pretty well. Do some background for the proton NMR here. Obviously the solvent is THF and it looks just like that. So just in case we have leftover THF, what does the NMR look like? And because you have a ring, the hydrogens that are above the ring and below it, and depending on the conformation that actually takes on at room temperature, you can get different absorptions. So it's not going to be pretty looking, triplets. You get 2 absorptions look like a gross multiplet, one just below 2, one around 4. So that is THF. Okay, so look for that in your final product when we get there. The other starting material is benzoic acid. There's not much going on here for hydrogens. It turns out when we ran this one I ran on our instrument, you can get better resolved ones that might show doublets or triplets on the internet, but right around almost 8 actually. Let me check that. Yeah, we had TMS that day, so this is very much the deal. We had 1.95, so 2 hydrogens were here, the other 3 were in this pile. So you'll see something like that. It turns out that normally what we say is the ortho positions, those 2 ortho hydrogens on the ring. When they're next to a carbonyl like this off the ring, those are the ones that get shifted further to the left. So that's what those 2 should be, the remaining 3 are those. And of course, the day I ran it, instead of getting a very broad, flat OH hydrogen signal, this one came out sharp and even integrated to 1 past 12. If somebody else runs it or other ones you get off the internet, it might be a broad peak. They're variable as always. You can't, this is a solid, had to be dissolved in some kind of solvent. So depending on the concentration, you're going to get various looking OH type hydrogens. The carbon, which we ran on our instrument, of benzoic acid. Now it turns out we did have an extra peak in there. which my gut is telling me, let's look at this. The carbonyl of the acid is the one that's furthest over here at 172. So that is the C double bond O carbon. And then normally, forgetting that little tiny one that's buried in there, maybe from an impurity, the detachment carbon should be the shortest, so arguably this one. What comes next is the two orthos. So 1, 2, 3, and 4. So I guess we would expect 4. So we have no choice but to say the shortest little peak, because we expect 4, is the attachment carbon. The one at the bottom, there's only one of them, we could argue is the next tallest peak. And these two, being similar in the tallest, we could simply say would be the two orthocarbons and the two metacarbons. Don't know which one is which, but that would sum that up. So that was benzoic acid. Turns out I do not have a carbon spectrum of benzyl alcohol handy. You guys should be able to handle that. I'm sure you can find one on the internet. Maybe I put one on a blackboard and I don't know about it, but at the moment I don't have a carbon of this beast. But I have a variety of different past students' protons of this, okay? So right off the bat, before I even look at it, I'm expecting to see the CH2 right there, the benzylic CH2. There should be a singlet. We see aromatic peaks, could be many, could all be one peak, don't know. And the hydrogen on the OH, I expect it to be variable. Sometimes it might show up, might be a nice little singlet, sometimes it's a broad peak, and sometimes you might not find it at all. So we centered on this peak right here. On the board, on the wall, we said it's at 4.6-ish. It should be a singlet. Turns out all the aromatic ones comes out to be almost a giant singlet. So there we go, the aromatic, oxa and bisons, and it integrates to a perfect 5. And it's almost like a giant perfect singlet for all the aromatics. So we wander this way. There is an integral of 2, and it does occur right at 4.6-ish. Clearly, you can see the tetrahydrofuran that's left over. And then we see this, see that broad peak right there? That could easily be, and it did integrate to almost 1 in their case, the hydrogen that was on the oxygen. What that little peak is past 5, don't know. The little peak at 2.1, is that a touch of acetone? Maybe some other stuff here that's not recognizable. So obviously what we're really looking for is the CH2, 4.6, and a nice big worth 5 hydrogen singlet right at 7.2 or 7.3. So let's look at other students. Shane and Stephanie, they get the telltale aromatic peak integrating to 5. They get a nice singlet at 4.6, but then there you get a nice singlet appearing at 4.1-ish and integrates almost to 1. That could be their OH signal. They have the remaining tetrahydrofuran. They even have a triplet of remaining ether. Quartet would be back here, but they had a little bit of ether left over as well. Next student, Justine and Carrie. Now you can see they get a little bit more broadening on their 4.6 singlet. See how broad that is? Almost as if it wants to talk to the neighboring OH, which could easily be that blob. Clearly has THF, clearly has a little bit of diethyl ether left over. That's the triplet. Angela, Gano, and James. What? Maybe they ran the spectra without spinning it, I'm guessing. So you get an integral of 5. There it is. It's ugly looking singlet. Yeah, right at 4.6, but notice how theirs, the entire thing integrates to 3, which means if they had spun this, I'm sure you get better resolution. The taller peak is the CH2. That little side hump is the OH one that happens to lump in with it, hence the integral. 2 big peaks, THF. Andy and Christina. What? I guess they probably should have labeled it as primarily THF, because that's what these two enormous peaks are. And hence the triplet and the buried quartet of diethyl ether as well. So basically their sample was almost predominantly THF and diethyl ether. And as far as the product, they get a tiny peak at 7.3 and the corresponding 4.6 peak. So they did not have much product whatsoever. And lastly, Elena and Joanne, they get a very nice singlet there at 7, a nice singlet at 4.6, small amount of THF, This peak at 1.26 down at 2. Acetone, water maybe. An OH being that far down could be 2, but see how the integral is 1.26. Can't tell definitively. Normally OHs for this compound and all the other students normally seem to be found to the left of 3. So whether that one is actually the OH of the compound, don't know for sure. So there we go, folks. Sometimes the OH will show up for you, and sometimes it might not. And it might look different in different ways. So that handles the NMR and the IR.